So now we'll take an example where kinetic energy and potential energy is acting on. So we'll take so when you're riding a bicycle, so turn to page number 133, figure 18.8. So once you ride the bicycle in a flat road, right? And you have a small hill. So you have to climb it, right? So when the bicycle uh, reached the bottom of the hill after riding along the flat road, it had some kinetic energy because it's moving. So it's moving when it goes up, right? Its kinetic energy decrease until it comes to a minimum value. So I think you have experienced this because once you when you ride the bicycle in a flat road and you come up with a small hill, like small slope, like not slope, small hill. So you have to ride the bicycle. Uh, you have to add some more energy. I mean, you have to put some more energy on the on riding the bicycle until you come to this point, right? So that means the kinetic energy is decreasing and it decreases up to a certain minimum value at this point, and you can just come to the bottom of the hill from this side. It moves down automatically. You don't have to ride the bicycle. So that means your kinetic energy decreases, and when you come to this position, your kinetic energy is zero. Not actually zero, it has a minimum value, but your potential energy is in a maximum value because you are in an elevated position. So you have the M means mass, you and your bicycle, and you have the gravitational force, and again you have a certain height. And once you come down at this position, your potential energy is zero because you don't have this height here. So once this H becomes zero, the mgh becomes zero. But your half mv squared, that means the kinetic energy is maximum at this point. Right? The same thing happens when you uh, in a moving swing. So you have a swing, right? And it comes to this position, that means, and it goes this side also, right? So once it is at this position, it's at a certain height. So it is in a certain. So at that position, your velocity is at a minimum value. That means I think you may have noticed this when you go back and when you go up. Um, your velocity or your speed is slowed down, right? But when you goes at this position, your speed is very high, right? So at this position, you are in a certain height. I mean, you are in an elevated position. So you have a certain height. So that's mgh here. But Do you have H here? No, 0. That means potential energy is 0 at this position, but your kinetic energy is maximum at this position because you are moving at a very fast speed at this position. But your kinetic energy is minimum at this position. Uh, I think you may have noticed when you go back, your speed becomes very low. Like you just it's like stopping there and comes back, right? So the same thing happens like the bicycle thing. So once you go, so when they give a picture like this, you have to remember that at this position your potential energy is 0, but your kinetic energy is at a maximum. Here at this position your potential energy is at a maximum, but your kinetic energy is at a minimum. Here also like that. Potential energy is high, kinetic energy is low. So we'll do an example. So turn to page number 134. The example number 1. Find the gravitational potential energy of an object of mass 7.5 kilograms at a vertical height of 4 meters. So potential energy is equal to mgh, right? So m is 7.5 kilograms, g is 10 meters per square seconds, h is 4 meters. So once you multiply 7.5 by 10, 75 and 4, it's 300 Newton, 300 joules, right? And the example number 2 also. Now you have to, if they have given the mass in grams, you have to convert it to kilograms, right? So if they have given in centimeters, you have to convert it into meters, right? So there is an apple or kind of a fruit, a tree. So the weight of that fruit is 200 grams. 200 grams, and it falls down 4 meters. The potential. You have to divide it by 1000. If you want to convert grams into kilograms, so if you have 3000 grams, that means if you divide by 1000, it will be 3 kilograms. Likewise, you have to divide 200 grams by 1000 in order to convert it to kilograms. And you have to multiply it by 10, and h is 4 meters. So then you get the number of joules. So now let's move on to the instances where potential energy is used in daily life. So water, even in our own houses, the domestic water tank is at a higher elevation, right? So when it goes up and up, the pressure of the water coming from the tap will be high, because once it goes up and up means the height becomes very high. Then the mgh becomes large. So once this energy is high, once it comes down to the ground level, it will come in a very high pressure, because it has a very high energy, because it is stored at a very high elevation. And the same thing happens in the water reservoirs. So normally when you the reservoir is at a higher elevation, but the powerhouse or the power station is the what do you call this, turbines are at a very lower elevation. So water stored in high reservation is allowed to fall down to a lower level, so transforming the initial potential energy. So in the tank or the reservoir, the potential energy is there, and once it falls down, the kinetic energy will be increased. So higher the elevation of the reservoir, and the lower the elevation of the turbines, the kinetic energy will be very high. The energy generated by the turbines will be very high. And the other thing is pile and tower. So I don't think you have seen this. So if you normally if you have this uh, in very large construction areas, so you have before laying the foundation, you have to what, tighten the loose soil. Otherwise what happens, it will, the soil will break down once you dig once you dig to have the foundation, to lay the foundation. So this is done by lifting the pile to some height. So look at your picture, look at the picture in the page number 135. So the pile, have you, did you see the pile? So pile, tower. So once you lift the pile to some height and releasing it to fall down onto the ground below. So higher the pile that you lifting, the higher the height that you lift the pile, higher the energy that is being released when it is falling down. So then the soil will be tightened very, I mean, the tighten will be very good. So sledgehammer is, I think you have seen this. You just put a wedge when cutting firewood. Um, an iron wedge is inserted into a piece of wood. So if you have a firewood like this, in Sinhala we call Dalapalana, right? So you have the large, say, large firewood, I mean huge firewood. You insert a wedge like this. The wedge is like this, just like a nail, larger than a nail, like this much. Uh, so an iron wedge is inserted into piece of wood that should be cut, and then you lift the sledgehammer. So once it is at this position, it has a potential energy, and when it comes down, the potential energy is very low, but its kinetic, the potential energy is converted to a kinetic, very high kinetic energy. So you can have a very high energy applying on this wedge, and once is so when a wedge is inserted like this, so it can, so this wood can be cracked from these sides, right? So Now we have come to the power. So power is the amount of work done in a unit time. That means you are doing a work for about 1 hour, and you have to take the efficiency, or not efficiency, the amount of work you've done, amount of work that you have done in 5 minutes, within 5 minutes, in 5 or in 1 minute, in 1 second, like that. So normally we take seconds. So if you need an hour to do some work, you have to convert that hour into seconds, and the work done will be in joules. You have to divide that work done in from the time. That means if you have done a work about 600 joules, and you have if you have taken 1 hour to finish to do this 600 joules, you have to divide this 600 joules by, if you want to find it by if you want to find it for 1 second, you have to convert this 1 hour to seconds. So how many seconds for a minute? 60. How many minutes? So 1 hour is comprised of 60 minutes, right? 60 minutes. So so you have 60 minutes. So how many seconds? For 1 minute you have 60 seconds. So 1 minute, 60 seconds. 60 minutes? How many? 60 minutes. You have to multiply 60 divided by 1 minute. Right? Then that means 60 into 60. That means 1 hour is comprised of 3,600 seconds. You have to divide it by 3,600, not 300, 3,600, 3,600 seconds. So power is, so the unit of power is J. When this S comes up, J, not simple S, capital J, simple S, J per second. That means joules per second. So we can derive, equation. That means work power is equal to work done divided by time spent in seconds. If it's in hours, you have to convert it to seconds. So let's look at an example. Example 1. The time taken to lift a mass of 5 kilograms to a height of page number 136. The time taken to lift a mass of 5 kilograms to a height of 8 minutes in 10 seconds. 8 meters in 10 seconds. Calculate the rate of doing work. So first you have to find the work, right? How do you find the work? Work is equal to force into distance moved. I'm not going to write the whole thing, but you have to write it. So the force, they have given the mass. Then how? Wow. So you have to calculate the force. That means 5 kilograms means you have to multiply it by 10. Distance, how many meters? 8 meters. Then 400 joules. How many seconds? 10 seconds. Then they ask you to find the power. Power is equal to work done divided by time taken. $400 to right. This joules per second is, we can give another form, that another unit, watt. Either watt or joules per second. Right? So the units are joules per second or watt. Capital W. So you can do the questions and you can look at the example number 2 also in the page number 137. So do the miscellaneous questions and that's the end of the lesson. So that is a very simple lesson. You can score from that lesson. So study that lesson.